Welcome, everybody. It's my pleasure today to introduce Fabian, who will be telling us about bridging persistent homology in discrete Morse theory with applications to shape reconstruction.
Thank you very much. And thank you, first of all, to the organizers for inviting me. I was really looking forward to my talk today, which is based on joint work with Uli Bauer about a project we published this year at SOZG. And since in my title, I'm promising you to bridge persistent homology and discrete Morse theory, I first of all want to briefly recall some aspects of both of these, and I promise I keep it very, very short, hopefully. So first of all, I want to talk about persistence. And then the way I want to do this here for now is that starting from a finite subset of RT, like a point cloud, I first want to connect the dots, meaning I, in this case, want to take the nerve of the cover given by closed balls, which you also know is a check complex. And as you're probably very familiar with, this does not just yield like one simple shell complex, but a whole filtration of simple shell complexes. And in persistence, we're usually interested in the evolution of algebraic quantities like homology and discrete, which you can interpret maybe as one-dimensional holes in your complex. And this we typically encode then combinatorially in the associated persistence barcode. Okay, persistence in one slide. Now I want to mention some key aspects of the computation that will be of importance later on. So let's say we have a very simple filtration. That is the simplex-wise filtration given on top of this slide, which is just a simple filtration of a two-simplex. And since this filtration is simplex-wise, we can consider the corresponding boundary matrix D equals R now in this first slide. And the procedure to compute, or one procedure to compute persistence is that check if there are any two columns with the same pivot and simply add the left column to the right one and record the base change in the matrix B and proceed as long as there are two columns with the same pivot. Okay, very simple. Now the thing I want to make you notice is that this column 7 was not touched by this very basic algorithm at all. And the reason for that is what we here call apparent pairs. And those apparent pairs are obvious persistence pairs. And I will give a slightly more detailed definition on the next slide. But the important part here is to notice that the algorithm doesn't touch these columns. And just as a reminder, you can read off the barcode for the simplex size filtration here simply by considering the non-zero columns in the reduced matrix R together with the pivots. Okay, so what is an apparent pair in slightly more detail? So apparent pairs are defined for simplex-wise filtrations, meaning for filtrations, where in each filtration step you are adding a simplex at a time. And then a pair of simplices, sigma I, sigma j, is called a parent pair or obvious pair, if you want, if sigma I is the latest proper phase of sigma j, which means sigma I is the largest facet of sigma j, and simultaneously you have that sigma j is the earliest proper cophase of sigma I, which is to say that sigma j is the smallest cofacet of sigma I. Now, why is this important in the context of persistence? Well, you can make an easy observation, namely that if you have an apparent pair sigma I, sigma j, then the interval ij is contained in the persistence barcode of this element-wise filtration, which is good and is also leveraged in some implementations of the persistence algorithm. Maybe you know Uli Bauer's RIPSA software. There it is used to shortcut the computation by a lot. Okay, so this was persistence. Now a brief detour to discrete Morse theory. And for those of you who do not know what discrete Morse theory is, in a nutshell, discrete Morse theory is a discrete analog of smooth Morse theory, which usually deals with functions on smooth manifolds. And now here in discrete Morse theory, we deal with functions on simple shell complexes, say. And in this context, a discrete Morse function is a monotone function on the simple shell complex that assigns, like in this figure I show you in the middle of the slide, that assigns to each simplex a real value that respects the phase relation. And additionally, you want that this function partitions the complex into pairs of simplices, which we usually denote by blue, like here, blue arrows. And you also have critical simplices, which are here, here in orange. And the reason why we usually denote these pairs with arrows is because that's what we interpret to be the discrete gradient of the discrete Morse function. So if you've never seen this before, maybe you're wondering, why is this useful? And this is useful because discrete Morse functions and also their gradients can encode collapses. So if we look at this example, what we can do is we can safely remove the simplices with function value 5 to obtain a smaller, simpler simplicial complex that still has the same homotopy type. And even further, we can now remove the simplices with function value 4 to get an even simpler simplicial complex in the end. Okay, so this is discrete Morse theory in a nutshell. And for later on in the talk, we will also need a slight generalization of discrete Morse theory, which is, well, fittingly called generalized discrete Morse theory, where the pairs in the discrete gradient are replaced by intervals in the phase poset. So if we consider the example from before and slightly modify this example, so in such a way that it looks like depicted here in the figure, where you now have 4 simplices with the function value 4, then those simplices form an interval in the phase poset, with the lower end of the interval being given by the top left vertex and the upper end of the interval being given by the entire unique 2 simplex in this figure. Okay, so what about connections between persistence in discrete Morse theory? On this slide, I want to give you some selected references, which you will be able to tell is very biased, but I want to go through them still very quickly. So the first thing, the first reference I found is a paper from Bauer, Lange, and Wardetsky that used a connection between persistent and homology for the optimal simplification of discrete functions on surfaces. And there's also a paper by Mishaikov and Nanda that used discrete Morse theory for filtrations to pre-process filtrations in order to get efficient computations of persistence. Now, I already mentioned Ripser, and I want to mention Ripser again, because like I mentioned before, Ripser uses a pair and pairs to shortcut the computation, because the pair and pairs are obvious persistence pairs, so you just know them from the combinatorics. And in the Ripser paper, it is also stated that apparent pairs of a simplex-wise filtration form a discrete gradient. So in this case, apparent pairs both relate to persistence and discrete Morse theory in a way. And then later on, like 2 years ago, in another sausage paper we wrote, we discovered another important observation that is actually important also for the things I want to talk about today in this talk. And as a side note, actually, this observation stems from this work. It's just kind of happened that the other work got published before. So the observation should actually be in the sausage paper from this year. And the observation is as follows. So say you start with a generalized discrete Morse function and the corresponding sublevel set filtration. Good. Then what you can do is you can, with respect to some arbitrary total vertex order, you can refine this filtration to a simplex-wise filtration. So that's something you can do. And then the zero persistence apparent pairs of this lexicographic refinement actually refine the gradient of the generalized discrete Morse function you started with. So in a nutshell, what this should tell you is there is a way to relate generalized discrete Morse theory to the computational aspects of persistence we are used to. And we are coming back to that later on. But before, I want to tell you about our connection, the connection we established between persistence and discrete Morse theory. I want to mention first the motivation for this project, which is related to shape reconstruction. And for that, I want to recall some other geometric complex that we typically use in TDA or in computational geometry, namely the Delaunay complexes. And in order to define the Delaunay complexes, we first start again with some finite point cloud, some finite subset of Euclidean space. And as depicted here, what you can do is you can first consider the Voronoi diagram. Like here you have a vertex, and what you see here going up to infinity, going here down, this is the Voronoi domain corresponding to that point. And the nerve of this cover given by Voronoi domains or the dual to this polyhedral complex is the Delaunay triangulation. And now in order to get the Delaunay complex to the parameter R, which you might also know as the alpha complex, which was introduced by Herbert Edelsbrunner, what you do is you intersect these Voronoi domains with closed balls centered at your point in your point cloud, and then take the nerve of this cover. And here's an illustration, so you see how this looks like. Now, in this talk, we are also very interested in a certain subcomplex of the Delaunay complex, namely RAP, which was originally introduced by Edelsbrunner almost 30 years ago as a subcomplex of the Delaunay triangulation for surface reconstruction purposes. And in this work, he used flow lines associated to Euclidean distance functions to define it. So it's not very discrete at first, but like later on, it was redeveloped using discrete Morse theory by Bauer and Edelsbrunner. And if you want to see an example now, like here are two pictures. On the left-hand side is the Delaunay complex of some point cloud for a small parameter choice. And on the right-hand side, you see the corresponding RAP complex to the same parameter choice. And what you should, of course, notice is that the RAP complex does a much better job of reconstructing the shape than the Delaunay complex does. So for example, especially here around the neck, it looks much nicer. Okay, so let's work our way to the definition of RAP. So an important observation that was made like 10 years ago by Bauer and Edelsbrunner is that the Jack and the Delaunay radius functions are both generalized discrete Morse functions. So what are the Jack and Delaunay radius functions? Well, there are two ways you can think about this. The first way is, well, these are the functions whose sublevel filtrations are the Jack and Delaunay filtrations. Okay, or if you like to have a more combinatorial interpretation, you could also say that the Jack radius function is the function that assigns to a simplex the radius of its smallest enclosing ball, and the Delaunay radius function assigns to a simplex the radius of its smallest empty circumsphere. And both of these functions are generalized discrete Morse functions. And then Bauer and Edelsbrunner went on to to establish that there exists a collapse from the Jack to the Delaunay complex, and then also from the Delaunay complex to the RAP complex. And you can also verify that this theorem is true if you look at these pictures, which I stole from their paper. So why am I mentioning all of this? Well, in the end, I want to tell you what RAP is in this discrete Morse theory language. And here is a remark. So this is not the way they are defining this they're defining RAP in the paper, but it's an equivalent one. Namely, you could say that the RAP complex is the smallest subcomplex of the Delaunay complex, such that the Delaunay gradient induces a collapse from the Delaunay to the RAP complex. So what this should tell you is that in some certain precise sense, the RAP complex is a minimal subcomplex of the Delaunay complex. Now, if you want to have a more explicit definition, I will give that now to you. So imagine you have this point cloud marked in red here, and let V be the gradient of the Delaunay radius function for this point cloud. So what you see also in the picture is, first of all, the Delaunay triangulation, and also there are small arrows indicating the pairs of this in this discrete gradient. And now the RAP complex is something that in our paper we'd call the descending complex of the gradient, and it is given by the smallest subcomplex of the Delaunay complex that A contains all critical simplices and B is the union of intervals. So what does this mean? So this example has three critical simplices that are now marked in color, and let's first consider this blue critical simplex. Now, because the RAP complex is a subcomplex, or is intended, well, we want the RAP complex to be a subcomplex of the Delaunay complex, we also know that we have to add its faces, right? That's just how subcomplexes work. And now, due to the second bullet point, we also know that we have to add these simplices that are now marked in blue. And if you go on, you see that this subcomplex you see now in blue needs to be contained in the RAP complex. And similar for the other two critical simplices. So everything that is in color now is precisely the RAP complex. Okay, enough formula, I want to show you some pictures. So here we have another point cloud in the plane, which was sampled from the contour line of a 2D bunny. Then here you see the corresponding Delaunay triangulation. Here are the critical simplices of the Delaunay radius function. Here the Delaunay complex to a small parameter choice. And here the rep complex to the same parameter. And I will go back and forth a bit so you can see the difference. And you can see that there are triangles in the Delaunay complex, like here, that are not there anymore in the rep complex. So again, the rep complex does a better job than the Delaunay complex itself, but there are still triangles, critical triangles here in the rep complex that you would not like to see. Okay, so what can we do about this? I want to switch gears now a bit and tell you about another method for shape reconstruction that emerged, as far as I can tell you, in the last years, which is homological in nature. And to this end, I want to briefly explain to you the exhaustive matrix reduction, and in particular the difference to the reduction I showed you at the beginning. So the exhaustive matrix reduction, also known as the total reduction, can also be used to compute persistent homology, in our case of the Delaunay filtration. And it proceeds as follows. And I will show you some details here. So the way we do this is, to compute persistence, we typically first need a simplex-wise filtration. And the way I want to do this here is I start with an arbitrary total vertex order. So this is an order on the point cloud, which then induces a lexicographic total order on the simplices, yielding a simplex-wise filtration. Just take this for a moment. Then, as before, we can use a variant of the Gaussian elimination to compute persistence. And in the way I want to do this now for the exhaustive reduction is basically the same as I explained to you before, but the key difference is here marked in orange. And this is the only thing you really need to remember from this slide. Namely here, this entry rjk, this does not need to be the pivot of the column rj, but it can be any non-zero entry. So in a nutshell, what you should remember is that the exhaustive matrix reduction tries to eliminate all entries of each column as much as possible instead of just the pivots. And as before, this will yield a reduced matrix R equals dV. And of course, as before, this determines the bar curve through looking at the non-zero columns of the reduced matrix R and the corresponding pivots. Okay, now there is a lot of things going on in this slide. And I want to apologize for that on the next slide, where I will show you an animation of how the exhaustive matrix reduction operates on a specific column of the boundary matrix that we chose. And I will first show you the animation, and then I will tell you something about it. Okay, so what do you see? So again, we started with a two simplex in the interior of the bunny. And what you saw is how the matrix reduction, basically how the matrix reduction operates on the boundary of this two simplex. And you see, while this algorithm proceeds, the boundary of the chain kind of flows towards the contour line of the bunny. And I find this very surprising, but because in this case, it really does a very good job of reconstructing the curve the points were sampled from. And hopefully at this point, you're deeply wondering yourself what this has to do with rep complexes, because like I showed you these two methods, so in both are built on the Delaunay filtration, so maybe there is a connection, and luckily there is, and I will tell you in 2 slides. But before that, I want to make some comments. So the first comment is that these cycles that they do such a good job at reconstructing shapes. We were not the first ones making observations in this direction, and the reference I want to mention here is the work by Cohen, Steiner, and co-authors, who considered in a sausage paper from 2 years ago, shape reconstruction from point clouds, where they use lexicographically minimal cycles, which are cycles that are in some sense minimal inside their homology class. And they also studied the connection to the persistence computation in the sense that they argued that the lexicographically minimal cycles are exactly those that are exhaustively reduced. But a key technical difference to our work is that they use a slightly different total order and simplices, refining the minimum and closing radius function, which basically means they're using a refinement of the check filtration. And while this is only a technical difference, it's still a bit unclear to me how their results relate to ours, which is still subject to further research, and I would be very interested to see how this is done. Then another loose end in the literature is that Foreman, in his original paper where he also introduced discrete Morse theory for cell complexes, defines a flow that can be associated to a discrete gradient, and this flow is a chain map. And later on, I will show you a slightly more technical definition, but for now, to get the understanding, it is enough if you let me convince you the picture that the flow does what it's supposed to do. So let's say you have a simple shell complex with a discrete gradient, like on the left-hand side, and you are considering a cycle that is here in orange. Then the flow is supposed to make the cycle follow the discrete gradient and map it to another cycle, like on the right. Good. Now, for the next slide.
Fabian, before you go on, let me ask a question from the chat. So can you remind us the definition of exhaustively reduced?
Yes, so it's basically using this procedure. Like you're taking pivots, the columns of your reduced boundary matrix, and as long as the you have an entry in your cycle that is non-zero, you add the column corresponding to the pivot entry to the column itself. So exhaustively reduced basically means obtained by exhaustive matrix reduction. I hope this answers the question. Okay, so good. Now, because we want to do persistence, we need a slight generalization of discrete Morse theory, which is for base chain complexes, and this was developed by several authors. And I won't dive into the details here, but it is only important for us to remember now that it is essentially the same as discrete Morse theory, but the basis elements take the role of simplices in discrete Morse theory, and all other notions translate basically straightforwardly. This is all. So it's basically like discrete Morse theory, but just in an algebraic way. Okay, so now I can tell you about our contributions about connecting persistence and discrete Morse theory, or some of the contributions. So first of all, we interpret persistence in terms of algebraic Morse theory, meaning we show how all of the persistence pairs form an algebraic gradient. Then what we also do is we show how the exhaustive matrix reduction corresponds to gradient flows, which is to say, we are making precise this movie I showed you before. Then we show that the lexicographically minimal cycles, which are related to this work by Cohen-Steiner and co-authors, are invariant under the algebraic gradient flow, which is good news because this brings the notion of lexicographical minimality closer to discrete Morse theory and therefore to the RAP complex. And lastly, we connect all of this to discrete Morse theory, or to generalized discrete Morse theory, and hence to the RAP complex through gradient refinements. And we do this, and I'm showing this technicality here, we do this by apparent pairs, which we learned about from the beginning when I talked about persistence computation. Okay, 2 comments. First of all, to all of these bullet points, except the third one, I will show you some more details later on. And the second comment is that all of these observations are general. So there's nothing really specific about Delaunay filtrations here. And also, like, each bullet point taken individually, it's not terribly hard to verify that it's true. But what it made it hard for us is that we had to develop all of these insights simultaneously and get the details right in such a way that in the end, all of this fits together and assembles to a proof of our main theorem, which states that the lexicographically minimal cycles of an inner Delaunay complex are always supported on the corresponding wrap complex. And I kind of find this fascinating because this notion of lexicographic minimality, there's an additional layer of algebra built on top of the filtration, which is to say you can add algebraic boundaries to cycles. And the magic is that the wrap complex somehow respects the structure while being a purely geometric object. And also, if you want to check that this theorem is true, because maybe you don't believe us, you can also look at these pictures we saw before. So on the left-hand side, we had this lexicographically minimal cycle we obtained from the exhaustive matrix reduction. And on the right-hand side is the wrap complex I showed you before. And you can check that the boundary of the blue two chain, which is this black line here, that this is actually supported on the wrap complex on the right. And so this is our main theorem, and we also made some experiments in higher dimensions, dimension 3, by using some small code we wrote, which you can also try out yourself if you want. And the way we obtained these good-looking cycles, I would say, is as follows. And the procedure is very simple, so you could also do this yourself. So first of all, take your favorite point cloud, like a sample from the Stanford bunny. That's step 1. Step 2 is compute Delaunay persistence using the exhaustive matrix reduction. Step 3 is take the bar in the barcode with the largest depth birth ratio, meaning the most persistent feature. You might wonder, why this bar? Well, this is heuristics, but the heuristics is this bar should kind of be born very early and die very late. So it should hopefully correspond to the fundamental class of the surface. And as a fourth step is you simply plot the persistent cycle corresponding to feature. And these are the cycles you get. So in a nutshell, you get these very nice looking cycles as a byproduct from the persistence computation if you do it in the right way. Okay, what do we know about these cycles? Well, first of all, we know that these cycles are lexicographically minimal, which relates to work of Cohen-Steiner and co-authors. And then we also know, due to our results, that these cycles must be supported on the wrap complex to a hopefully small parameter. And we don't even have to construct the wrap complex to know that. So this is what we know. And as of future work, we're still very interested in getting more insights about the cycles and also their topological and geometric properties. But this is still to be done. Okay. This was the end of the expository part of the talk, and in the remainder of the time, I would like to show you some technical aspects that I personally find interesting. And first of all, what I want to do is I want to explain to you how persistence pairs form an algebraic gradient. So to this end, what we do is we first consider R equals dV, the reduced boundary matrix of a simplex-wise or element-wise filtration. And then if you've done enough topology or algebra, you know that you can use these columns to decompose your filtered chain complex into elementary indecomposable summons. And you basically do this as follows. So you take non-zero columns of the reduced matrix R and the corresponding column in the base change matrix V, and then the chain complex I wrote here constitutes a summand of the filtered chain complex. So this is what we know, because so this is all we do also when we do persistence. And if you know this, you might come to the idea that it would be nice to try the columns the tuple Ri Vi for all I, and actually these form an algebraic gradient, but unfortunately, or interestingly, depending on your point of view, this is not the right thing to do in this context. But the right thing to do is something else. Namely, what we do is we consider what we call the reduction gradient. And there, instead of considering the whole column Ri, we just consider the corresponding pivot. And now, rightfully, maybe you're asking yourself, what is he telling me? Well, maybe let me try to explain why this might make sense. So if you think back to classical discrete Morse theory, there you also would never pair a simplex with its entire boundary, which is very much in the spirit of the first bullet point, but you would always pair a simplex with its largest facet, which is very much in the spirit of the second bullet point. So in order to relate discrete Morse theory and persistence, I think this is the right thing to do. And you can also make this a little bit more precise. And the remark goes as follows. So say you have an ordinary discrete Morse function, so not a generalized one, just an ordinary one. And you consider the corresponding sublevel set filtration. Okay, then you can simplex-wise refine the sublevel set filtration, and you can consider the reduction gradient for that. And when you do this, you actually notice that this reduction gradient I just explained to you actually extends the discrete gradient of the function you started with. So in some sense, you can view persistence as an honest extension of discrete Morse theory in this case. Okay, so now we know how persistence pairs can be interpreted to be algebraic gradient pairs. And I want to explain now to you how the exhaustive matrix reduction actually corresponds to gradient flow in the sense of Foreman. And for that, I need to show you some technical details now, because otherwise this does not make sense. So I want to remind you of the algebraic flow that you can assign to in this case, algebraic gradient. And to this end, let us look first at this map F here. So what is this map F? So this map F is supposed to do the following. So on the basis element, it is supposed to map this basis element to the basis element tau if sigma tau is contained in your gradient. This is what the map F does. And if you work over fields that are not F2, then you need to worry a little bit about coefficients, but let's ignore this for now. And then the algebraic flow is defined as follows. So you take the identity first on your chain, meaning the chain C itself, and add it to the boundary of f of C plus f of boundary of C. Now, if you have never seen this before, this might look very awkwardly maybe. So let me make two remarks, and hopefully then it's getting a bit clearer. So first of all, by construction, this map F is a chain homotopy between the identity and the flow phi. Okay, so in particular, this flow acts on cycles in a very special way. Namely, there the flow reduces just to C plus boundary of f of C, like here, and therefore acts on each homology class of the chain complex by a change of representative cycle. Okay, if you want to have a picture, let's take this example from before again. And there we have that this edge in the cycle is paired with this 2 simplex. So in particular, this boundary of f of C is the boundary of the 2 simplex, of the unique 2 simplex in this example. So if you add this now to your original chain, you get the chain on the right. Okay, but this is not a talk about the basics of algebraic Morse theory, but I want to show you how this looks like in our case. And I want to hopefully convince you that this is actually essentially the same as the exhaustive matrix reduction does. Henry, you have a question?
Yeah, there's another question in the chat. Is the Morse cancellation operation the same as reduction gradient in discrete Morse theory?
I'm not sure if I understand the question correctly.
Yeah, let me try one more time. I hope I'm reading this right. Is the Morse cancellation operation the same as the reduction gradient in discrete Morse theory?
Reduction gradient in discrete. So I'm not sure what reduction gradient in discrete Morse theory is. So maybe we can try to postpone the question, and maybe the person asking a question can speak up later on. Oh,
That sounds good.
Thank you. Okay, so exhaustive matrix reduction and gradient flow. Again, I want to start with R equals dV, a reduced boundary matrix of an elementary situation. And for the sake of simplicity, just let's take F2 coefficients. So it's getting easier. And we're doing this nevertheless all of the time. So now, first, I want to remind you of the reduction gradient. So first of all, the pairs in the reduction gradient are given by the pivots of non-zero columns in the reduced matrix R and the corresponding column in the V matrix as depicted here. Then we can start computing. So let's apply the flow to a cycle. Then what you get is first the cycle back plus some sum. And in this case, we sum over all pivots of the reduced matrix R, take into account the corresponding non-zero entries of the cycle itself, and multiply that with the boundary of f of sigma I. And here sigma I is the birth simplex of this feature. Okay. So what to do next? Okay, so how does this gradient work? So this gradient takes a birth simplex. In this case, it's denoted by pivot Ri, and it pairs it with the corresponding column of the base change matrix V to the depth index of the feature. So this boundary f of sigma I just evaluates to a column V with the depth index of the feature I. Okay. How to go on? Well, now it's easy. So we want to simplify this equation, this boundary of f of def I, and this is just because R equals dV, this is just given by the corresponding column in the matrix R. Okay, so to summarize, what did we learn? Well, if you want to apply the flow to a chain, what you do is you first consider the non-zero entries of the chain, see if there is a pivot in your reduced matrix R that corresponds to that, and then you add it to your chain. And this should very much remind you of the procedure of the exhaustive matrix reduction. And as a matter of fact, you can also show that the stabilized cycle associated to the cycle, which is the cycle you get by iteratively applying the flow as long as there is something changing, and at some point there's nothing changing anymore, that's the stabilized cycle. You can show that this stabilized cycle is actually the corresponding exhaustively reduced cycle. So in that way, if you set it up correctly, you will see that there's a tight connection between exhaustive matrix reduction and the gradient flow of the reduction gradient. Okay. Last technical slide, I promise. So there are a bunch of general insights we made that lead to our main theorem. And the first insight is that smaller gradients have more flow invariant cycles, which is to say that if you have a algebraic gradient W and P, and you should read P to be the reduction gradient, then you have that the cycles that are flow invariant with respect to P that are also flow invariant with respect to W. Then there is a analogous statement in the geometric world, like in the simplicial complex world, meaning that if you have a discrete gradient W that is a regular refinement of a generalized discrete gradient V, and regular means that every non-critical interval in V is also is partitioned by non-critical intervals in W, then the descending complex of W is a subcomplex of the descending complex of V. And the way you should read this proposition is that V is the gradient of the Delaunay radius function, and W is the zero persistence apparent pairs gradient. Okay, we are almost there. there's another statement that I find interesting, namely that if you have a non-generalized discrete gradient on a simple complex, then their associated flow invariant chains, which are an algebraic object, they are actually supported on the descending complex of W. Okay, 2 more steps. The first 2 propositions can be connected, as I mentioned before, by the fact that 0 persistence apparent pairs are contained in the reduction gradient. And the other 2 propositions are connected by the fact that 0 persistence apparent pairs refine the generalized gradient. And in our application, we have in mind that this generalized gradient is the gradient of the Delaunay radius function. So this is what we do in the paper, and this is actually the proof strategy of our main theorem, which then shows that the lexicographically minimal cycles, which can also be expressed as being the chains, the cycles invariant on the flow associated to the reduction gradient, so which kind of lives here on the top in this object, is actually contained in the wrap complex, which in this case is this object. Okay. At the end of my talk, I just want to make a brief summary of what we learned in our work or in this presentation. Is first of all, we provide a tight link between persistent homology and discrete Morse theory. And we do this in such a way that the corresponding algebraic gradient flow can be viewed as a variant of the reduction algorithm for computing persistence. And the second thing we learned is that these general insights can be used to establish a strong link between Morse-theoretic and homological approaches to shape reconstruction. And more concretely, what we prove is that the lexicographically minimal cycles of a Delaunay complex are supported on the corresponding wrap complex. And with that, I'm done. Thank you very much.
All right, so before we get to questions, let's briefly unmute ourselves and applaud for the speaker.
Thank you all.
All right, questions for Fabian? Guillaume, please go ahead. Guillaume, are you able to unmute yourself?
Hi, I have a question about applications. So, did you try applying your algorithm in more noisy data? So, we saw that you tried it on those nice point clouds that forms nice shapes, but if there's more noise, does it still work?
So we also, of course, I didn't show you in the talk, but we also tried another point cloud from the Stanford library, namely this horse, if you know that. And the point cloud is more noisy and it didn't work quite well, but you could still see all of the necessary pieces are kind of there. It's just not the most persistent feature anymore, but maybe they are among the first 20 most persistent features. And the procedure didn't work, but it seems like you can still use information you gain from persistence to reconstruct the shape as a whole. But this is still an idea we're still about to pursue.
Thank you.
Thank you.
Jose, please go ahead.
Yeah, Fabian, first of all, great talk and really good work.
Thank you.
So first I wanted to make sure that I understood the main theorem. So what you're saying is that if you're using the Delaunay sort of complex filtration, and so then and then maybe the next one, the corollary from that. Yeah, that if you look at the cycle that corresponds to the longest bar, then that it is geometrically nice if you're doing an exhaustive sort of reduction.
So this is that it is geometrically nice is still an open question that we would like to answer in the future. Because by now we just know that this is lexicographically minimal and that is supported on wrap. And hopefully along this we can develop more insights that actually lead to also geometric reconstruction theorems. But this is still a very wide open question.
I see. So yeah, it's just that it's supported on the wrap. Okay, so
Yeah.
thank you for clarifying, because my question was going to be, how is this connected to like minimal bases? Not in the lexicographical sense, but in the sense of sort of geometric predicates.
Yeah. So honestly, I don't know.
Yeah. Okay. And then if I can sort of, yeah, go ahead.
Yeah, just maybe still to clarify, like this is here more like an experiment. The big theory, like the theorem we proved, the main theorem is this one. And the other is like just heuristics and like experiments to demonstrate that maybe in the future you can even do more with that.
Yeah. Okay. Then sort of the other question I had was, how particular is this to the Delaunay triangulation or the sort of alpha filtration? I'm asking for example, the diameter function for the Rips complex. Does that give you like a discrete Morse function?
The diameter function for the root. I'll answer this in two sentences. So the first thing is the theorem we prove in the paper is slightly more general than this, because basically this works for every generalized discrete Morse function, but then you have to replace rep with the corresponding descending complex, which might be different than rep, of course. That's the first answer. And the second answer, so the diameter function is not always a generalized discrete Morse function for RIPS. It's just in very special situations. But if it is, I mean, you can plug it into our more general theorem and you get something. It just don't know how useful this is then.
I see. So you don't know what the complex is for RIPS in those cases.
Yeah, I mean, it's what we call a descending complex, but I have no idea if this is of any use in a sense.
RIPS is huge. So yeah, thank you.
Yeah, you're welcome.
So Fabian, I'm going to read this question in the chat. So curious to know if there's any connection between the reduction gradient and the Morse cancellation operation. Because in Morse cancellation, we are canceling critical simplices if there's a unique gradient path.
Yeah. So first of all, now I understand the question. Thank you for clarifying. But unfortunately, the short answer is I don't know. Sorry that I can't answer the question.
No, honesty is the best policy.
Yeah.
Can I ask a question?
Of course, please.
First, just to confirm about the reconstruction. So to do the reconstruction, you have to use the Delaunay filtration, right? So then other filtrations probably would not work.
In what sense other filtration won't work?
I mean, if you want to like very nicely reconstruct like a 3D mesh or like the silhouette of the point cloud, then
I mean,
have you tried other filtrations, other type of filtrations, or are you have to use the Delaunay filtration?
Okay, thanks for the question. First answer is I haven't tried any other filtrations because like this Delaunay filtration fits nicely with this language of discrete Morse theory. But this is work of Cohen-Steiner and co-authors. They're actually using something, well, it's related to both, but it's more like check filtration. And they're using, it's more, they're using kind of check and lexicographically minimal cycles there. And in their work, they're also arguing that this works nicely. And it's still an open question to relate this to what we are doing.
Okay, so my other question is, so how this reconstruction compared to other reconstruction algorithms? Because I think reconstruction is a very well-studied problem, right? So how it compares to the other reconstruction algorithm?
Yeah, I don't know.
Okay, got it.
But
thank you.
Like, I would say for me personally, the theme of this work was more like to show that there were these two different methods. And if you view it from the right angle, they were very tightly linked. And
Yeah. I know. But I think it's very interesting. Yeah. Anyway, it's thank you for the talk.
thank you. And maybe to clarify, I also don't claim that what we're doing is like the best you can do, but because there are a lot of clever things you can do, but it's just more about this connection of different methods that hopefully in the future might lead to better insights to shape reconstruction or these two methods.
Further questions?
Yeah, maybe you want to follow up on the questions we already had. Talking about what would happen if you use a different filtration. So if you could use, instead of the Delaunay filtration, the check filtration, then you said I have to replace the wrap complex by the descending complex. But I was wondering, didn't you say that the check complex can be kind of collapsed to the wrap complex through the Delaunay complex? So is the descending complex of the check complex now the same thing as the wrap complex?
Very good question. I don't think so. And it is still a very interesting question to me as to how these collapsing results by Bauer-Edelsbrunner relate to what we are doing. Because there might be a connection that in the end you can still say, so I'm widely conjecturing now, but maybe this lexicographically minimal cycles considered by Cohen-Steiner and co-authors, which is based on check filtrations, essentially, that you can still prove that they're supported on the wrap complex. But how to do that, I have no clue.
Yeah.
But it would be
thank
very
you and thanks for letting us ask questions that go a bit more in the wild direction. Of course, perfectly fine if you don't know everything. I'm curious.
That's a part of the seminar, I guess.
Exactly.
Can I have a question too? If there is still a bit of time. So you were at one point you mentioned this heuristics that you choose like the biggest bar. So okay, as far as I know, you sort of cannot prove that it always works nicely, right? It's probably generally strange thing to expect, like to expect the proof of that. But did you find an example where it like didn't work at all, or did it just like always work and you think actually that's the right way? It's just not proven.
So it always looked like it has something to do with the original shape. Maybe it was a bit bulky, maybe a bit deformed if the sample is not dense enough, say. But I haven't seen an example where it went in the totally wrong direction. Yeah.
Okay, thank you. I mean, it would be interesting to somehow formalize, make this more formal.
Yeah, exactly.
Yeah.
Especially since
Okay.
now you have this work on the reconstruction of shapes and stuff.
Yeah. Yeah. Okay, thank you very much.
Thank you.
Any final questions?
Maybe one. How is the wrap complex computed in practice?
That's difficult, but I guess you would just I guess you would just take the one second.
So you follow the recipe in your definition?
Yeah, so I guess I don't know how you would do this in a clever way, but I would do this by computing, the Delaunay gradient.
Okay.
And then basically following this procedure I explained before.
I happen to know that there is some software by Katharina Elsbeck. It's called Rep23, and I think in her PhD thesis she described how she computes it. And if I remember correctly, she had some iterative algorithm where she adds always one point after another and updates the Rep complex. But yeah, it's written in her thesis, I'm pretty sure.
Is it
Thank you, Terry.
Rep23?
Yeah, Rep, like Rep complex, and then 23 like the numbers.
Okay, great. Thank you.
You're welcome.
She was Herbert's student, in case you have trouble searching for her.
Guillaume, I think you might have had another question. Please go ahead if so.
Well, actually, it was more of a comment than a question, but just want to say that I've been really interested in your work, and I've read those papers about the descending complexes, and I've been trying myself to implement them, but in another setting with the what we call multi-dimensional Morse functions, so with vector vector values instead of real values. And I hope I get some results similar to yours eventually with those other type of functions. If I don't have any theoretical results yet, but I've been implementing it, so I hope we get something soon in that area too.
Yeah.
And yeah, so just want to say I really appreciate your work. You've been doing
Thank
lots
you.
of nice results.
I appreciate it, really. Thank you.
All right. Well, thanks again, Fabian, for the fantastic talk, and thanks everyone for the nice discussion. So let's end the recording here.